we've been thinking about superpositions in oscillators and in wave packets, these may be superpositions of energy eigenfunctions. Indeed, to make it easy to see what happens in time, we've deliberately chosen such superpositions. Now, previously, we had said that if something was in a single energy eigenstate, then it had a very definite energy. But what is the energy now for our oscillator or our particle if it's in a superposition of such energy eigenstates? To answer this question, we need to go back to the idea of quantum mechanical measurement. This is a subject that is still philosophically very tricky and is the subject of considerable debate. However, from a practical point of view, how we handle this is quite straightforward, even if there's some philosophical doubt about why we can get away with this. We can find the key to the practical resolution of this problem if we recollect what we said about the interpretation of the wave function. There we said that we would take the approach that the probability of finding the particle at some point was proportional to the modulus squared of the wave function near that point. Now we're going to generalize this concept, a concept that, as we said before, is known as Born's rule. So let's see how this works.
Suppose, then, we take some normalized quantum mechanical wave function, psi of r and t. And we're going to expand it in some complete orthonormal set of spatial functions, psi n of r, at least at some time t. And if we allow the expansion coefficients to vary in time, we can keep doing this at every other time t. And so we know we can always do this. And our arbitrary quantum mechanical solution of Schrödinger's equation can be written like this: an expansion in terms of this orthonormal spatial basis and a set of expansion coefficients that vary in time. And this wave function we're going to presume remains normalized, by the way. The fact that this psi of r and t is normalized means that we know the answer for the normalization integral. Whatever this is when we take the modulus squared of it, then we can write that out in terms of these expansions here. Here's our psi of r and t, and this is psi star of r and t. And if we integrate up this whole thing here, it will come to 1. Note, incidentally, when we are multiplying two different wave functions that are both expanded, we have to use different indices for each of these summations here. Because of the orthogonality of these basis functions here, in each of these expansions, they're all orthogonal to one another, only the terms with the same index on both sides survive. If this was psi 1 star of r and this was psi 3 of r, the integral of the product of these two would just be 0. But if these have got the same index, then the integral, of course, of these, the product of them over space, will be 1. So all the terms where the n index over here matches the m index over there survive this overall integration. Because these wave functions are normalized, in other words, this is by choice an orthonormal set of basis functions, the result from any one of these spatial integrals where n is equal to m will just be 1 for that spatial integral, and so at that particular time we will just be looking at the product of these two coefficients, and hence that will be Cn of t all squared. Hence, this proves for us that if this is to be a normalized wave function, the sum of the modulus squareds of these expansion coefficients always has to equal 1. That's a consequence of our insistence that this wave function here is normalized.
In quantum mechanics, when we make a measurement on a small system with a large measuring apparatus of some quantity such as energy, we find the following behavior, which is sometimes elevated to a postulate or a hypothesis in quantum mechanics. On measurement, the system collapses into some eigenstate, maybe the nth eigenstate, of the quantity being measured. Mathematically, we imagine we expand the state of the system in the basis set that is that set of eigenfunctions of the quantity being measured, with expansion coefficients Cn. Then, the probability that the system collapses into a specific state n is the modulus squared of this expansion coefficient Cn. We just proved, incidentally, that the sum of all these modulus squareds of these coefficients Cn adds up to 1, as we would require if these modulus squareds are to represent probabilities. Now, you might be a bit disappointed that we are not actually going to explain this strange collapse phenomenon here. There are several reasons why we're not going to do that. First, to understand why this is a philosophical problem, and in what way it's a philosophical problem, it's best to leave this until we understand more about how quantum mechanics works. Until we do that, our questions would have little meaning, and we might not understand the proposed answers that do exist. We would just be descending into mysticism. Second, from a practical point of view, this rule, which as we said can be called Born's rule, just turns out to work very well. As long as we consider it merely to be an empirical observation for measurements made by large systems and small ones, this approach always seems to give us the right answer experimentally. The third and perhaps most important reason for not explaining this collapse phenomenon is that we actually don't really know the answer. Resolving this measurement problem has been a continuing activity in quantum mechanics up to the present day. The branch of quantum mechanics that deals with these problems is known as measurement theory, and the core problem is known as the measurement problem. Modern pictures of these resolutions are much different from those originally envisaged in the early days of quantum mechanics. Nonetheless, they are still confusing, and one thing we can say about all of the proposed resolutions is that they are generally all bizarre in some way or another. So, for the moment at least, don't worry about why this is the rule or where it comes from. Just learn it and use it. Treat it as the way we are going to predict things in quantum mechanics, and also how you as a student are going to complete problems successfully and get good marks and good grades as a result. So let's look explicitly at the measurement of energy and the kinds of results we're going to get.
Suppose then that we do some experiment to measure the energy E of some quantum mechanical system. We could repeat this experiment many times, each time preparing the system the same way before doing the measurement. And it would appear from our proposition of Born's rule that we're going to get a statistical distribution of results here. We will get probabilities Pn of getting a specific energy eigenstate with energy En as the result of the measurement. If that is what is going on, we would get an average answer for the energy, which would just be the following. We would multiply each energy by the probability of getting that energy in the experiment. The sum of all of these would just be the average energy. That's a normal statistical statement. And we are saying that we are taking these mod Cn squareds to be the probabilities. So therefore, we would say that on the average, the energy we would measure, if we did such an experiment, would be this expression here. And we call this average the expectation value in quantum mechanics. That's also an expression in statistics, but we're rather explicit about using this idea in quantum mechanics. And the expectation value has these strange angled brackets round about the quantity we're measuring. So this is the expectation value of E. It's simply the statistical average based on the idea we're using Born's rule to establish these probabilities. So let's look at an example of calculating an expectation value. And we're going to look here at a state that we looked at before, the same one we used when we were thinking about having harmonic oscillators actually oscillate. And that coherent state, you remember, has a parameter capital N in it. And in that case, the modulus squareds of the expansion coefficients are just these coefficients here, these expressions here. And this expression, incidentally, happens to be the probability that you will receive little n letters if on the average you receive capital N letters every day, for example. It's that piece of statistics. Anyway, these are the expansion coefficients modulus squared here from our coherent state with parameter capital N. Now, we know the answer for what En is. It is h bar omega times n plus a half h bar omega. So we can rewrite this here as h bar omega times little n times this expression. And we know the answer to that one, and the answer to this summation here happens to be capital N, and we know that answer because this is just the Poisson distribution in statistics, and we can look this up. So the average number of letters that you receive every day is going to be the number of letters you receive on a given day with the probability that you're actually going to receive that number of letters on a given day from the Poisson distribution. And the answer for the Poisson distribution is this number, capital N. Anyway, whether or not we understand how to do this summation here, we can get the answer to it, and the answer happens to be capital N. So that tells us that if we're in this coherent state that we discussed before, with this parameter capital N, the expectation value of the energy, the average value we will get if we keep setting the system up in the same coherent state and doing this measurement of energy, that average value will be capital N plus 1/2 times h bar omega. So that's the expectation value of the energy if we happen to have put a harmonic oscillator into a coherent state with this parameter capital N. Note here that n does not have to be an integer. N can be any real positive number. This is an expectation value, not an eigenvalue. The eigenvalue would have to be an integer number plus 1/2 of these h bar omegas. But this expectation value in this parameter n does not have to be a discrete number. We can have states with any expectation value we want. We can set them up so that we would get any particular expectation value you want. So although this is a quantum mechanical system, in this superposition state, it's not constrained to have just discrete values of energy.
At this point, we are setting up our way that we are going to handle quantum mechanical calculations. Calculations that will give us statistical answers as to what results we will get out of experiments. We've just been saying that when we set about to measure the energy of some quantum mechanical system, one that's in a superposition of energy eigenstates, then each time we try to do the experiment, with the system starting out in exactly the same superposition state, we may get different answers. Each of these answers will correspond to an eigenstate. Before going any further, we need to confront what we are doing. We need to see the apparent absurdity of what we're saying. A classic experiment that forces us to do this is what's called the Stern-Gerlach experiment. This is an experiment that measures not the energy of an electron, but another property called spin. Spin is a property of an electron that, among other things, means that the electron actually behaves like a tiny little bar magnet. In fact, most of the strong properties of magnetism in materials come from this property of electrons. We will have to postpone a more detailed discussion of spin itself for some later time. For the moment, we're going to look at an apparatus in which we fire electrons through a magnetic field to see how they're deflected. This deflection, and our subsequent observation of a dot on a screen, constitutes our measurement of spin. We're going to look at what this collapse of the state from measurement looks like here. The consequences of our measurement postulate here are perhaps rather surprising and not what we were expecting classically.
So in our Stern-Gerlach experiment, we have an apparatus with some magnetic material in it, some magnets. And we're just showing the north pole end of a magnet and the south pole end of it. Of course, they have to be joined round in behind, but we're not showing that. So we've got a magnetic north pole here and a magnetic south pole down here. And we imagine we've got a screen of some kind over here, and we've drawn the center line in here just for reference. And an important point about this apparatus is that it's deliberately set up to have a non-uniform magnetic field. Why is it non-uniform between these plates here. In fact, it's different up here than it is down there. Why is that? It's because you see we've sort of wedged down this north pole here. So the magnetic lines of force, if you like, are a little bit more concentrated up towards this north pole than they are down near the south pole, because we've sort of wedged this magnetic north pole a little bit. So they're more concentrated in here. It's a locally stronger magnetic field up near the north pole in the middle than it is near the south pole in the middle of the magnet. So the magnetic field is more concentrated here than it is down there. So now we imagine we've got a collection of little bar magnets here. These are little small magnets, and they've got north and south poles on them. And in this case, I'm drawing one where the south pole is upwards and the north pole is downwards. And of course, as usual, a south pole is attracted to a north pole, and a north pole is attracted to a south pole. So we're going to take these magnets and we're going to imagine firing them through here, and we're going to see what happens. And this is just a classical experiment we're thinking about for the moment. So we fire them initially along this dashed line. Now, because the magnetic field is non-uniform, that is, it's stronger in here than it is down there, this little south pole is slightly more strongly attracted to the north pole than this little north pole is attracted to the south pole. And as a result, a magnet oriented like this, fired through here, will be deflected up. The south pole is slightly more strongly attracted this way than the north pole is attracted down the way. And if I were to reverse the direction of this little bar magnet and put the north pole at the top and the south pole at the bottom, this north pole would be slightly more strongly repelled from this north pole than this south pole would be from this south pole. And so, in this case, the magnet would be deflected down. And if we had a horizontally oriented magnet, it would see no net deflection. There's no net force on this magnet in here. Doesn't really matter that the field's stronger here than it is in here. There's no net force because the north and south poles are equally close to both of these larger north and south poles. And we would think that magnets of other orientations, if we don't know what they are in here, they're going to be deflected by some sort of intermediate amount, maybe not all the way up here or all the way down here, but somewhere in the middle. So after firing many randomly oriented magnets through here, we should end up with a kind of a line of results, the magnets hitting anywhere along this line here. Now, that's fair enough, but what happens when we use electrons in this experiment? Well, electrons have a quantum mechanical property called spin, and that spin gives them what we call a magnetic moment. That means the electron behaves like a tiny little magnet, kind of like those little bar magnets we were showing. So what will happen if we fire electrons through this apparatus with no particular starting orientation of their spin? So these are like randomly oriented electrons. We're not preparing them in any particular way. And we fire them into our Stern-Gerlach apparatus. We might expect to see a line on the screen, just like we saw with the randomly oriented ordinary classical magnets. Incidentally, I should say that the actual experiment here used silver atoms, but in this sense, in this particular way, they behave the same as electrons do. Well, with electrons in our apparatus, we fire the electrons in here, and what we get on the screen is 2 dots. So with our randomly prepared electrons, the result is either the electron lands up here or the electron lands down there. It never lands anywhere in the middle, even if the electrons are completely randomly prepared, with no particular orientation of their spin. How do we explain that? Well, I don't think we explain it, but we say it fits in with what we've been proposing. We've been saying that when we measure something, we collapse it into an eigenstate of the quantity being measured. Here we're measuring the vertical component of the electron spin. And there are two eigenstates of the vertical component of the electron spin. Those eigenstates are spin up and spin down. So we have collapse to the eigenstates. This is a measurement apparatus of some kind, and when we send the electrons through here, we are measuring the vertical component of the spin, and that means, quantum mechanically, we collapse that state onto one of the eigenstates. It either has to be a dot up here or a dot down there. And this is quite unlike the classical situation, and it's very difficult for us to understand this, but it's completely consistent with our proposal about what quantum mechanical measurement does, even though we don't understand why it does that, and we don't even know the mechanism in general why that works.
We now see the shocking result of our measurement hypothesis. Apparently, this measurement of the vertical component of the spin forces the results to be only one of two outcomes, one of two dots on the screen. And here is another shocking result. If we were to rotate the whole apparatus, the positions of the dots on the screen would just rotate as well. There was, in fact, nothing special about our choice of the vertical direction here for our apparatus. There's no special vertical direction overall in space, and gravity itself is having a negligible effect in our experiment. If we've rotated the entire apparatus, in that case, the apparatus would be measuring the spin along another axis, and we would be forcing the electron to collapse into one or another of the different eigenstates now oriented along this different axis. For example, we could rotate the apparatus by 90 degrees, and the two dots would be left and right on the screen instead of up and down. To make this weirder, for spin, the same quantum mechanical state of the electron can be expressed as a linear combination, a superposition, of up and down, or strangely enough, left and right, or even forwards and backwards. Whether or not we understand the details of spin here, the key point here is that now that we are measuring spin along some axis, we are also forcing the collapse of the state into one or another of the eigenstates, up or down, or left and right, or forward and backwards even, of the quantity being measured.